Let me first of all explain to you something concerning this book. First, you can buy it. It's not very expensive. I will give you the address. But more important, I was very happy that I negotiated with the editor. The editor is my institution is ENS Edition. And I succeeded in negotiating with them that the PDF file of the book is free. So there's a technical problem. They want, and I understand that they want to produce a PDF file which is somehow locked. That is, you cannot print it, or you cannot extract pages from it. Anyway, so I have the PDF file. And the editors is taking a long time to produce the protected PDF file. So officially, I'm not entitled to give it to you. But I'm becoming tired with the non-efficiency of the editors, so I give them one more week. And after one more week, I promise I give you one address you can download the PDF file. Okay? After all, when we wrote the book, we did everything, and the editors have only to lock the PDF file. So, well, that's okay. Okay, so let me remind you where we are. There was this theorem of Riemann, according to which any simply connected, bounded, non-trivial, simply connected domain in the plane is biholomorphic to the unit disk. The proof of Riemann was based on this minimization of energy that he called the Dirichlet principle. This Dirichlet principle is okay, but it took a long time before we could find a proof. And after Riemann, people were complaining because the proof was not solid. And the most serious complaint came from Schwarz, who tried to find some alternate proof of this Dirichlet principle. So I told you that Schwarz did essentially two things. First, he tried to understand how to solve the Dirichlet problem or the conformal representation in the case of polygons. And the success was full in the case of triangles. I will explain that today. But more importantly, Schwarz created the idea of the alternating procedure, alternating method, which allows you to solve the problem for two domains, for one domain which is built out of two domains that intersect on a simply connected domain. And I will begin by explaining to you this method, this alternating method of Schwarz, which has been very much generalized later by people from numerical analysis, not only for this problem, but for a vast category of elliptic partial differential equations. So it's something that not only proves the existence, but again is very much constructible. You can put it on a computer and you get explicitly the solution of the partial differential equation you want. So for example, if you give me a surface triangulated, then this is exactly what Schwarz was doing. You can really construct with a computer, you can construct the conformal representation. So I want to begin by explaining roughly, not in detail, the idea of this alternating method. I will present it in the most complicated situation, which is the following. Suppose you have a surface which is covered by two open sets. This is one open set U, and the other open set is V. And you assume that both open sets U and V can be represented conformally to disk, let's say with a continuous extension to the boundary. So you have a conformal representation from, let's say, phi U, from the open set U to the disk, and you have a conformal representation phi V from the lower open set to the disk. And you assume that in between and the intersection of the two open sets is homeomorphic to some annulus. And the idea, the question is, show that with this information you can construct a global conformal representation from the surface to the round sphere. So you want to glue these two conformal representations in a single one to produce a global conformal map. So the trick is very simple. It will be constructed by some limiting procedure where you will try to solve alternatively the problem for upper and lower domain. And you go to the limit and you get a solution. So let me explain that. Well, if you want to construct a conformal mapping from this surface to the sphere, what you really are looking for is a global complex coordinate Z belonging to C union infinity. Say the north pole is infinity and the south pole is 0. So what you really look for is a holomorphic map on U having a single pole in some point, a holomorphic map on V, and these two this meromorphic and holomorphic maps should agree on the annulus. So you want to match them on the annulus. So by definition, we know it's easy to do on U, it's easy to do on V, but of course if you pick a function at random here and here, there is no reason to coincide on the intersection of the two. So you have to fix that. So here's the trick. First, you start with U. And you define, let's say, U0, or let me call it, let's say F0, is a function of U to the real numbers that will be defined as being log of phi, let's say, of modulus of phi of Z. So you take, in U, you have a map to the unit disk, you take the value, take the log of the modulus. This is a harmonic function which has a pole at the origin, which has a pole at this point, the point which is mapped to 0. Now what you do is that, as we did yesterday, you restrict your function f0 to the boundary of U. You get a continuous function on the boundary of U, so you can extend it harmonically inside U. So you extend it harmonically. Let's say F0 bar is the harmonic extension. And then you let U0 to be, by definition, F0 minus F0 bar. So what is it? It's what I called yesterday a green function. It is a harmonic function on U with a pole and which is 0 on the boundary. So U0 is harmonic on U minus this spatial point star which is mapped to the origin. And u0 on the boundary of u is 0. So this is the green function of the open set u. Now you want to go, did I make a mistake? What? Two u's. U is, I'm sorry, no, that is a, two u's? Where?
There's a capital U and a small u, but that's no problem.
Ah, this is small. This is, small u is a function defined on big U. What?
It's a zero on the boundary of u. You can take it only.
Of course, you're right. It's already 0, you mean. It's already 0. You are right. Marco is right. You start with, sorry. Is it what I want to do? I start with 5e. No. This, what I did was ridiculous, but I start with f0. I did too much. u0 is the function log of 5e. Okay? So it's a harmonic function on u, which is 0 on the boundary. Yes. Then I look on v. On v, I have a function u0 which is not defined everywhere, but which is defined in the annulus. So I can restrict u0 to the boundary of v. I restrict u0 to the boundary of v. This is a continuous function on the boundary of v. Therefore, I can extend it harmonically inside v. And I define v1, or v0 maybe, yeah. I define v0, by definition, is the harmonic extension of u0 restricted to the boundary of v. Then I go back again to u. This function v0 is a harmonic function on v. So I can look at it on the annulus and restrict it to the boundary of u. So I can define u1 to be the harmonic extension of the restriction of v0 to the boundary of u. And so on. This is why it's called alternating procedure. At each time, you take the previous function, you look at this function on the other open set, you restrict it to the boundary, and you extend it harmonically. Now, I'm going to show you why this is a converging procedure. So what I'm going to show you, or at least to sketch proof, is this. I claim that the series converging uniformly. So each time you do that, you get a smaller and smaller functions, and I claim that this defines a converging sequence. Assume this is true, then I can call this sum U, and this sum V. Maybe infinity, something like that. And I claim that these functions U and V are exactly what is required to solve our problem. That is, to construct a meromorphic function on the global surface. How do I do that? Look, we have the boundary of U, boundary of V, and boundary of U. So by definition, I started with U0. U0 is 0 on the boundary of U, but is not 0 on the boundary of V. By definition, V1 or V0 is equal to U0 on the boundary of V. This definition. So, by definition, U1 is equal to V0 on the boundary of U. And each time you have equality, this one, this you have V0, V0, U1, then you have U1. Let me put it this way. U1 is equal to V0, V0 equal to U1. Then you have V1 is no. At each step, one is equal to the other. So when you take the sum of all the ui's, that is what I call U infinity, and when you take the sum of all the vi's, that I call V infinity, they coincide on the two boundaries, boundary of V and boundary of U. Am I right? So we have two harmonic functions. U infinity is a harmonic function on U. V infinity is harmonic function on V. And these two harmonic functions, when restricted to the annulus, coincide on the boundaries. Hence, they are equal. Okay, you have a harmonic function on an annulus. You have two harmonic functions on the annulus. They are equal to the boundary by the maximum principle. They are equal everywhere. So these functions are equal. And then we are done. I mean, we use these functions U infinity and V infinity as we use this. Did I make a mistake again? But V0 has U0. No. V0 has no. Why? No. V0 is the. What I'm looking for is the real part of Z. No, I want the real. I'm looking for the real part of this coordinate. So you are right. So I take real part I started the wrong way. Is the real part of is that better? No? No, because harmonic is not harmonic at this by the point star. Okay? It is? Yeah, but this, you have something against that? Do you have something against that? What I'm looking at, okay, I want to construct a global coordinate on my surface, okay? I want to construct Z. Z in V will be Z, and in U will be the inverse. Okay, so on U, I consider the real part of 1 over 5. This is a harmonic function in the complement of 0. Has a pole at 0. On V, I want something really harmonic with no singular point. So I play this game, I take these sums, and finally I get a harmonic function on the full sphere with a pole at the North Pole. Okay? And this harmonic function is the real part of a holomorphic function, and this holomorphic function is the global uniformization I was looking for. Is Marco convinced? You are? Good. Because if Marco is convinced, then this is correct, I think. Okay. Okay, so maybe I was not clear enough. Okay, so, okay, we have this manifold covered by 2 charts. You have one candidate for coordinate for the first one candidate for coordinate for the second one, and we want to construct a global coordinate in C union infinity. So in V, I will take, as a first approximation, I will take phi V, but in U, as a first approximation, I will take the inverse of phi U. These 2 coordinates do not agree on the intersection, so I try to fix this problem on the intersection by modifying in this way. And this is obtained by this limiting procedure.
Where does phi V enter into your calculation?
Phi V? Well, because it enters everywhere. Because, when I said I take the harmonic extension of V 0 respect to yes, but each time I have to use the chart to come back in the disk. You see, if I have a...
I don't see anywhere where you use V.
To define that. So what does that mean to extend harmonically a function in the interior? So I want to extend harmonically a function given on the boundary of U. How do I do? I have a function defined on the boundary of U. I have to use phi U or phi V to have a function on the boundary of a disk. And then I use the Poisson extension. Do you see what I mean? When I say I take a continuous function on a curve, I extend it harmonically inside. How can I do that? In order to do it, I need phi U to transform my problem in the surface to a problem on a disk. And on a disk, I know how to do it. Do you agree? U0 could be any harmonic function, but I need this one at the end to get really what I want. It could be any harmonic function having a single pole having a single pole, but there is only one, this one. Paul, do you agree? Look. I am playing the game of solving alternatively Dirichlet problems. The only case in which I know how to solve a Dirichlet problem is on the disk. Because for the disk, I have the Poisson formula that gives me explicitly the solution. This is the only situation where I know how to do it. Since I have these two open sets which are covered by two charts, phi u and phi v, each time I have to solve, to extend harmonically a function on a curve, I have to put it back to the plane to make it a disk for which I can solve the solution. Is that clear now? Okay? Okay. Okay, so again, I insist on that. If you know how to, this is completely explicit construction. A computer can do it quickly. Now, let me give you just a quick idea why this series is converging. So why is well, there is a very simple observation first, that this is at least a decreasing sequence. It is clear that UK plus 1 is less than UK. That's not enough to guarantee convergence, of course, but that's already something. Because each time, how do you pass from UK to VK? Well, you extend harmonically some function. You have a function on a circle, and you extend it harmonically on some inner circle. So the sup norm is decreasing. So it is clear I shouldn't say that. And I should say the sup of UK plus 1 is less sup of UK. Because it's just a maximum principle. But of course it's not enough to guarantee convergence. But the key property that makes the convergence is the following inequality that today we call Harnack principle. Harnack principle. But this is, of course, already in Schwarz, which is the following simple idea. Take a function on the circle. Assume, for example, that the average value is 0, and extend it harmonically inside the disk. And then evaluate this harmonic extension in a subdisk with radius is given, say rho. So we evaluate the norm of U bar of Z, where Z is in a disk of radius rho. Of course, this is less by the maximum principle than the maximum of U on the circle. But the Harnack principle says that if you know the size of the disk rho, you can improve this quantity here, and you can put here a quantity epsilon of rho, where epsilon of rho is strictly less than 1. So this is the main idea. If you take a continuous function on the boundary, assuming the average value is 0, if you harmonically extend it to inside the disk, then you can be sure that the value on the disk of radius rho is very small, much smaller than it was on the circle, and this very small is controlled by the rho. And that's exactly that will make the procedure of Schwarz converging, because each time you apply the procedure, you always have some control on the space between the unit circle and the place where you extend it harmonically. So each time you apply the system, the thing is convergent geometrically. So this shows that this sequence of functions uk are decreasing, converging to 0 at exponential velocity. So I will show that to you. That's very easy. Look, suppose we know the Dirichlet formula. We've seen that yesterday. It tells us that u bar of z is given by the Poisson nucleus. It's u of I e theta d theta. And here I have a kernel. And the kernel, I remind you, is this. Maybe there's a 2 pi here. Yeah. Okay, so now let's try to evaluate u bar of z when we know that the modulus of z is in the disk of radius rho. So look, this is the unit disk. This is the disk of radius rho. And z is somewhere here. Exponential of I theta is somewhere here. So what can I say? Well, the numerator is between 1 and 1 minus 4 squared. And the denominator is the distance between z and exponential. So the denominator is at most 1 plus rho, maximum distance, and at least 1 minus rho. So if I square it, so the nucleus here is close to 1. The nucleus I'm looking at, 1 minus z squared is at most 1 minus 4 squared, and at least so you see that this quantity is really close to 1 in a completely explicit way. That means that u bar of z minus u bar of 0 which is the 1 over 2 pi integral of 1 minus what? U bar of 0 is 0 because, U bar of 0 is 0. But anyway, I'm right. You see that this quantity here is bounded by a function only depending on rho. And I can compute it here. I think it's 2 rho. I think this is less than 2 rho. I think this is what it is, but that's not important. Let me call that this quantity is less than epsilon rho. So you get that if U bar of 0 is 0, you get U bar of Z minus modulus is less than epsilon of rho sup U of Z. Okay, so that's very simple. If you look at the Poisson kernel, when Z is equal to 0, it's 1. So when Z is equal to 0, it's just the famous formula that the value at the origin of a harmonic function is the average value on the boundary. If Z is not 0 but close to 0, this quantity is not 1 but close to 1. Close to 1 in a uniform way. Which means that you can compare the value at Z with the supremum by this quantity which is explicitly small. Okay, so it's very, very simple idea. If you take a continuous function on the circle, you extend it harmonically inside. If the average value is 0, what you get in a small disk is uniformly small. And so when you look at this procedure of Schwarz, each time you go from UK to VK to UK plus 1 to VK plus 1, this is a procedure which is really converging very fastly, very quickly to 0. And so when you take the sum, it is indeed converging fast enough to impose the uniform convergence. Of course, there are details to check, but the idea is really very, very simple. And again, this is not related to holomorphic functions or even to dimension 2. This is something which has to do with elliptic operators in any dimension. So this is a standard numerical way to solve elliptic partial differential equations piece by piece. If you can solve it in this piece, you can solve it in this piece, then you can solve it in the union of the two pieces. This is a simple and great idea. So I did that in the case of two open sets overlapping on some annulus, but you could also do it on two open sets overlapping on some other open set, simply connected set. And in the same way, you would prove that if you are able to map conformally this to a disk, this to a disk, then your union of the two, you can map it to the disk. So this is something very, very beautiful and simple. And again, that you can put in practice. So for more details, I mean, all the details and all the epsilons are in the book. Okay, so Schwarz was happy to be able to glue solutions, so he needed examples, and he looked at the triangles. So I want to explain to you now what Schwarz did. No, I didn't use. I used the assumption that I knew. Okay. You're here. Okay. What he proved is that if you can map conformally one open set, one other open set, if the intersection is an annulus, you can do globally. Now, if you take a surface and you can cover it by small balls. These small balls, if they are small enough, you can map them conformally to the disk. So by induction, you glue them one by one, and you get the full picture. And this is not using Riemann mapping theorem. This is just by induction. There's basically no analysis there. Just, okay? So, Schwarz looked at triangles, polygons, and even circular polygons. So a circular polygon is a polygon whose sides are arcs of circles. Here's a circular polygon. And he wanted to find, if possible, explicitly map from this kind of polygon to the disk, or from the disk to the polygon. So let me explain what he did. Well, first of all, he started a priori believing that the theorem was true, because after all, this was published by Riemann. So let me begin by, let's say, polygon. You have a polygon, which is given, and you assume that you know the angles. So I will call the angle lambda 1 pi, lambda 2 pi, so lambda n pi. So these are the angles. So I will suppose here that the lambda i's are less than 1. And you assume that Riemann is right. So you assume that there is a conformal mapping from the disk to the polygon. And I want to show you that there is no much choice. There is only one possible formula for it. And what he did is this. Instead of taking the disk, you take the upper half plane, which is of course the same. And so you will assume that you have this map, phi, going from the upper half plane to the polygon. And you will assume that there is a continuous extension to the boundary. So you will have points A1, A2, A3, AN minus 1, which are mapped to the vertices etc. So each point AI is mapped to a vertex. And why did I put A minus 1 and not AN? Because I can always assume that the point AN is the point at infinity. So I will assume that. The point AN is the point at infinity and is mapped to the nth vertex, lambda n. Okay, so what Schwarz does is that he introduces what I call, I learned a few days ago, it's called the pre-Schwarzian derivative. Schwarz defined the following thing. He looked at the derivative with respect to z of log phi prime z. So it's a holomorphic function defined on the upper half plane. And Schwarz observed that this holomorphic function has to extend holomorphically on the full plane minus the points A1, A minus 1. So why is it so? Well, this is precisely the place where Schwarz introduced his famous symmetry principle. I think you know this interesting lemma in complex analysis. You have a holomorphic map, let's say psi, defined on the upper half plane with values in the upper half plane. And you assume that when you converge to the real axis, you assume that psi is converging to the real axis. Then you define a map on the full complex plane by taking a point in the lower half plane, taking it symmetric with respect to the real line, taking its image, and then taking it symmetric. And you define a map psi from the full plane to itself by this definition. And Schwarz's principle is that if you start with a psi which is holomorphic, then the extension is holomorphic. This is even a local theorem. If psi is holomorphic in a neighborhood of the real axis and has this property that when you go to the real axis, the image goes to the real axis. If you play the same game, you extend it holomorphically to the symmetric of this open domain. And then, if you believe this symmetry principle, which is easy, you will apply that immediately to this pre-Schwarzian derivative. And the reason is this. Look at this function, d dz log phi prime z. And restrict it to some interval ai plus 1. Let's look at what's happening here, or in this neighborhood. Well, the map phi is mapping this side ai plus 1 to a side of the polygon. This is our assumption. This A2, A3, for example, is mapped to A2, A3. This side of the polygon might not be the real axis, but by some affine transformation, you can make it coincide with the real axis. So if you take psi, you arrive in C, and then you make some suitable affine transformation in such a way that this composition now maps alpha z plus beta. This goes now to the real axis. So you post-compose psi with an affine transformation in such a way that after the composition, the psi that you are looking at is mapping AI plus 1 to a segment in the real axis. So if you do that, you can apply the Schwarz reflection principle not to psi, but to psi composed with alpha z plus beta. But this gadget here has been invented by Schwarz exactly to be invariant under affine transformations. So if I define, let's say, psi bar of z to be alpha psi z plus b, beta, it is kind of obvious that when you compute derivative, psi bar prime of z, it's of course alpha psi prime of z, take logarithm, take derivative, and this disappears. So this differential operator is just the right clever trick to be insensitive to post-composition by affine transformations. So therefore, this function ddz log psi prime c does extend holomorphically to the lower half plane. Because you can do that for any AI plus 1. So the result of that is what I said here. This function extends holomorphically in the complement of these points A1, A2, AN. Okay. Now, we want to understand what's happening in the neighborhood of these points AI. We want to understand the behavior of ddz log psi prime of z. How does it behave as a holomorphic function in the neighborhood of these points A1, A2, AN? This is the place where you have to use that this transformation phi in the neighborhood of AI has to change this angle pi in an angle lambda pi. So what we expect is that in the neighborhood of AI, the function psi looks like z to the lambda. So in the neighborhood of AI, we have something like that. Psi of z, phi of z, is of the order of z minus AI to the lambda times some holomorphic function of z. In the neighborhood of AI. This is just because we know that the angle at the vertex AI, which is here on the left-hand side, is pi, has to be multiplied by our transformation by lambda to make it lambda pi. So we have this formula. And then we make a computation for phi prime, compute log, take derivative, and you get the local behavior of this function in the neighborhood of AI. And you get that this function has a pole with a residue, how is it? The residue is lambda I minus 1 is equal to lambda I minus 1 over Z minus AI plus holomorphic. Yes. So we know that our function ddz log phi prime, which is a function which is holomorphic everywhere except possibly at the AI, has actually a pole of order 1 at each of the point AI, and the residue is lambda I minus 1. So that means that if we take the function d dz log phi prime minus sum of lambda I minus 1 Z minus I, this is now a holomorphic function with no singularity in the plane. It's an entire function. Because it's holomorphic everywhere. It's holomorphic everywhere, including AI. Now the last step is to look at what's happening at infinity. So you look in the neighborhood of infinity. Then you have the same game, because I assumed, as told you, that the last vertex an is at infinity. So at infinity, I have an angle lambda n pi. So we have at infinity a behavior for phi like z to the minus lambda n. And then you compute again derivative, log derivative, derivative of log derivative, and you deduce from that that this function is bounded. In the complex plane, hence is constant. And the result of this deduction is this. This is the theorem of Schwarz. It is the following. If there is a conformal map from upper half space to a polygon with angles lambda 1 pi, lambda n pi, then this phi satisfies d dz log phi prime z is sum lambda I minus 1 z minus ai. But be careful, in the spirit of Schwarz, this theorem is conditional to Riemann mapping theorem. At this level, Schwarz does not know that there is a conformal map from the polygon. He says if there is one, it has to satisfy this differential equation. And then if you have such a differential equation, you can solve it by double integration. And you get the following formula, which is the so-called Schwarz-Christoffel formula, that tells you that phi of z up to a constant has to be constant times the integral from z0 to z of the product dz z minus a1 lambda 1 z minus a2 lambda 2 z minus a n minus 1 plus constant, there's a 1 minus. Plus constant. Okay. Just by taking the primitive of this function, exponential, and primitive again. Now let me make a few comments. If we are looking for triangles, well, the good fact about triangles is that their shape is completely determined by the angles. If I give you the angles of a triangle, I know the shape. So the lambda i's are given. I'm looking for two values of a1, a2, because a3 is at infinity. And these 2 points, a1 and a2, of course, I can change them by some affine transformation of the line. So I can always assume that a1 is 0 and a2 is 1. And then I get the formula, phi of z is constant integral dz z 1 minus lambda 1, 1 minus z minus 1, 1 minus lambda 2, plus constant. And you see, you are happy because you give me a triangle, where you give me the angles, lambda 1, lambda 2, lambda 3. I give you the conformal representation. This is a formula, explicit formula, for the conformal representation of a given triangle by the upper half plane. So from that point of view, Schwarz is happy, has completely described the case of a triangle. For a polygon, it's much more complicated because you don't know where the points AI should be placed. You can put A1 and A2 in 0 and 1 if you wish. But you still have these unknowns. Where should I put A2, A3, A4, etc.? The point is that a polygon with more than 3 vertices is not determined by its angles. So if I give you let's say a quadrilateron, if I give you a quadrilateron with the 4 angles, of course the angles are not enough to deduce the shape of the quadrilateron. So I give you the quadrilateron, I give you the sides, okay? And now you look for a conformal representation. Okay, I can put A1 is equal to 0, A2 is equal to 1, and then I have some freedom from A3. Where should I put it? For each choice of A3, this formula will give a conformal map on a certain quadrilateron with the right angles, lambda 1, lambda 2, lambda 3, lambda 4. But how do I know that there is at least one A3 for which I catch the right rectangle I'm looking for? And this, Schwarz could not do it. He couldn't see any reason why, for any quadrilateron, there could exist a coefficient A3 such that this map for this A3 maps to this quadrilateron. And then he just had to find this alternating procedure to solve the problem by gluing two triangles. You can construct, by gluing together several triangles, you can construct quadrilaterons or pentagons or polygons in general. And then he had a proof of Riemann theorem in the case of polygons. Hence he knew by this formula that indeed it was the case that choosing correctly the AIs, you could match any given polygon. But he could not prove that directly. A direct proof of that will be given by Poincaré 15 years later. And I think you can guess it. The direct proof of Poincaré will be qualitative. You will prove it by some continuity argument. But Schwarz did not think of that at the time. Okay. Anyway, so again, in the idea of Schwarz, he would have been delighted to prove with such a formula that you can match any given polygon, but he couldn't do it. He could do it for triangles because a triangle has no degree of freedom. There is no moduli. Only the angles give the triangle. Polygon, you need more. You need sides, length. And then Schwarz went to the other problem of looking at conformal representation not of polygon but circular polygon. So now you have something like that. Oopla. You have a polygon, but the sides now are not segments anymore. The sides are circular arcs. And now you again have an angle, lambda 1 pi, lambda 2 pi, lambda n pi. And again, I think you understand that you have much more freedom for circular polygons than for polygons, because you can connect the vertices by circles, and circles have more degrees of freedom than segments. So what Schwarz does, and what he did was at the same time as Christoffel. This is Schwarz, and now what I'm going to tell you is Christoffel and Schwarz, independently. Well, they had the same kind of technique. You look for a conformal map from the upper half space minus a certain number of points to some circular polygon, phi, and you want to play exactly the same game as before. You want to use the symmetry principle of Schwarz. I told you before the idea when we had the polygon was to say, well, I take AI plus 1. It is mapped to a side of the polygon. By a suitable affine map alpha z plus beta, I can map it to the real axis. And then there was this trick that the operator ddz of log phi prime was non-sensitive to affine transformation. Now, of course, if you have a circle here, you cannot map it to the real axis by an affine transformation. But what you have to do, what you can do, is to use a Möbius transformation. Möbius transformation that will be alpha z plus beta, gamma z plus delta. So there's a suitable map, suitable Möbius transformation that will map your circular arc to the real axis. So what Schwarz does is says explicitly, I need some differential operator that would not change under post-composition by Möbius map. And this is where he creates the Schwarzian derivative. So Schwarzian derivative was invented exactly for this purpose, to find some differential operator which is invariant when you post-compose it with a Möbius transformation. So you take a function phi, z, and then you take psi of z is equal to alpha phi of z plus beta divided by gamma phi of z plus delta, and you want something that applied to psi or to phi gives the same value. So while you take derivative, one derivative, two derivatives, three derivatives, you eliminate coefficients. In the paper of Schwarz, it's very unclear what he does. But of course, he ends up with the so-called Schwarzian derivative of phi, that, as you know, is third derivative am I right? I think this is it. Okay, so you define this, and you check. This is the way Schwarz does, with no intuition, just computation. You check that this is indeed equal to S of psi. And once you have this tool of Schwarzian derivative, which is insensitive to change of coordinate by Möbius transformation, you can play exactly the same game. You prove that the uniformization you are looking for has the wonderful property that its Schwarzian derivative extends holomorphically to the plane minus the points AI by the same symmetry principle. The symmetry principle plus the invariance of Schwarzian derivative implies that the conformal mapping we are looking for has the property that its Schwarzian derivative is holomorphic in the plane minus the vertices. Then again, you know that in the neighborhood of the vertices, the map has the form lambda I times a holomorphic function of z, because it has to multiply the angles by lambda I. Then you look at the behavior of the Schwarzian derivative of such a function in the neighborhood of AI, and you look at infinity, exact same construction, and you get finally the following theorem. Theorem. Schwarz. Christoffel. If there is a conformal map from upper half space to some circular polygon, then its Schwarzian derivative has to be equal to, it's just a little bit more complicated than before, but not so complicated, has to be equal to sum 1/2 1 minus lambda I squared z minus ai squared plus beta I z minus ai where the beta i's are unknown and satisfy some conditions. So I write it here. The sum of the beta i's is 0. The sum of 1 minus lambda I square plus beta I ai is 0. And 3, the sum of ai 1 minus lambda I squared plus beta I ai squared is 0. And the beta i's are real numbers. You see here the situation is even more complicated. You are given the circular polygon. You know the angles, which are the lambda i's. And what Schwarz and Christoffel did for you is that they give you an explicit differential equation of the third order whose solutions will give you the conformal representation to the polygon. However, you know the lambda i's, you have no idea of where should be the ai's, and you have no idea of what should be the beta I. And it is totally unclear, at least for Schwarz and Christoffel, it is totally unclear that given a circular polygon, it is possible to choose in a convenient way the ai's and the beta i's in such a way that the solution of this differential equation gives you the conformal representation on the polygon you want. However, indirectly, Schwarz knew it was true because by his alternating procedure, he knew that all circular polygons have some conformal representation to the disk, and hence there is some ai and some beta I for which the problem is solved. But again, these beta I and ai's in differential equation, they are called the auxiliary parameters. We will meet them again when you look for Fuchsian equations later. So this is a half success for Schwarz and Christoffel. And actually, numerically, it's very hard. If I give you a circular polygon, I give you everything. I give you the centers of the circles. I give you where they meet. I'm going to give you the coordinates. And I ask you, please, could you find the ai's and the beta I for which this is the solution? I know no good numerical solution. I know no constructive proof of the existence of these coefficients. The only proof I know is some kind of fixed point theorem or non-constructive way. The only constructive conformal maps I know for that are given by the alternating procedure. You can approximate them as much as you want by this alternating procedure, but I know no way of finding directly the correct differential equation that gives you the conformal representation. Okay, so I stop here. Let me tell you what's next. So then, so far we have discussed local uniformization is Gauss. And we have this global theorem for surfaces which are homeomorphic to a sphere. Then we have to go to higher genus, and that will be the next part of the game. We will meet Klein and Poincaré next Monday. Okay, thank you.